Long before calculators fit in pockets, arithmetic was something people physically operated. A mechanical calculator was a machine built to perform basic arithmetic through moving parts, gears, wheels, drums, levers, carriages, and later keyboards. These devices did not think in the modern electronic sense, but they could automate repeated addition, subtraction, multiplication, and division with a level of speed and reliability that mattered enormously in offices, tax departments, engineering work, commerce, astronomy, and navigation. The problem they solved was not abstract curiosity. Human calculation was slow, repetitive, and easy to get wrong. A single column of figures could contain a tiny error that changed a tax bill, a table of prices, or a scientific result. Mechanical calculators were attempts to turn arithmetic from mental labor into a controlled physical process. Their story is also the prehistory of computing itself, because many of the ideas later associated with computers first appeared as mechanical problems: how to store a number, how to carry tens, how to repeat an operation, and how to make a machine follow a sequence. One of the first major breakthroughs came in 1642, when Blaise Pascal built the Pascaline. Pascal was not just inventing for amusement. His father worked as a tax collector in Rouen, and the job involved large amounts of tedious arithmetic. Pascal understood that the most exhausting part was not the idea of addition, but the constant handling of digits and carries. If a column reached 10, the next column had to increase by 1. Humans did that automatically, but a machine had to do it reliably through mechanics. The Pascaline used wheels to represent numbers, and its most important achievement was a workable tens carry mechanism. When one wheel completed a full rotation, it could advance the next wheel. That sounds simple, but in metal and brass it was difficult. The machine had to move cleanly, avoid jamming, and preserve accuracy. Pascal's device showed that arithmetic could be embodied in hardware. It was not yet an office revolution, but it proved the concept: numbers could be made mechanical. A generation later, Gottfried Leibniz pushed the idea further. Beginning in 1672, he designed the stepped reckoner, a machine intended to handle more than simple addition. Its key component was the stepped drum, later known as the Leibniz wheel. This part contained teeth of varying lengths, allowing a gear to engage by different amounts depending on the selected digit. With that mechanism, a machine could perform repeated addition more efficiently, making multiplication and division practical as mechanical procedures. Leibniz also introduced important design ideas: a movable carriage, cursors that effectively preserved an operand, and a two-motion design that separated setting numbers from operating the calculation. He built versions in 1694 and 1706, and although they were not mass-market products, their influence was huge. The Leibniz wheel appeared in calculating machines for roughly 2 centuries, even surviving into the compact Curta calculator of the 20th century. Leibniz was not merely building a gadget. He was imagining calculation as a system. The 18th century brought a wave of inventors who tried to build machines capable of the 4 basic arithmetic operations. Names such as Philipp Matthias Hahn and Johann Helfreich Müller belong in this chapter. Their devices could be impressive, and some worked very well. But there was a hard economic barrier: precision mechanics was expensive, slow, and unforgiving. A calculator needed many parts to align perfectly. A slightly misshaped gear tooth or poorly fitted axle could produce wrong results or jam the whole mechanism. Because of this, many machines remained unique pieces, built for patrons, rulers, or collectors. They were often admired as marvels in cabinets of curiosity rather than used as everyday business tools. Müller's 1783 machine was an exception because it was used to tabulate lumber prices, a reminder that practical demand existed. The limitation was not the usefulness of mechanical calculation. The limitation was production. The machines were valuable, but still too difficult to make in quantity. The real commercial turning point arrived in the 19th century with Thomas de Colmar's arithmometer. Manufactured from 1851, it became the first mechanical calculator strong enough, reliable enough, and practical enough for daily office use. This mattered because a calculator is only transformative when it can survive routine work. A delicate demonstration machine impresses visitors, a reliable office machine changes habits. The arithmometer could assist with arithmetic in environments where repeated calculation was unavoidable, and for decades it dominated the market. In fact, for around 40 years, it was essentially the only type of mechanical calculator broadly available for sale. Its success showed that mechanical calculation had moved from invention to industry. It also revealed what users truly needed, not just clever mechanisms, but durability, repeatable accuracy, and a format that clerks could learn. The arithmometer turned mechanical arithmetic into a commercial product and opened the path for competing designs. By the late 19th century, the field accelerated. The Oedner arithmometer, industrially produced from around 1890, became highly successful and helped broaden the market. Around the same period, new input methods changed how people interacted with machines. The comptometer, introduced in 1887, used a keyboard made of columns of 9 keys, one column for each digit position. Instead of turning cranks and setting wheels in older ways, trained operators could enter numbers quickly by pressing keys. This made mechanical calculation feel closer to clerical data entry. Then, in 1902, the Dalton adding machine introduced the 10-key keyboard, a layout that feels familiar because it anticipates later calculators and numeric keypads. These keyboard machines mattered because speed was not only mechanical, it was human. A machine that was accurate but awkward could slow an operator down. A better keyboard changed workflow, reduced friction, and made calculators more useful in busy commercial settings. Mechanical calculators also began to absorb power from the electrical age. Starting in the early 20th century, some machines used electric motors to drive operations that had previously depended on hand cranks. This did not instantly make them electronic calculators. The logic of the calculation was still mechanical: gears engaged, counters moved, and carries propagated through physical parts. But motorization reduced operator effort and increased speed. It is an important distinction because the decline of mechanical calculators did not happen overnight. For decades, machines became hybrids in practice, mechanical systems assisted by electric power, refined for office productivity. They belonged to a world of accounting departments, insurance companies, government offices, and engineering desks. The machines could be heavy, expensive, and specialized, but they formed a serious industry. Their design evolved around the same pressures modern technology faces: user input, reliability, speed, maintenance, and cost. The difference was that every improvement had to be solved in matter, not code. While office calculators developed commercially, Charles Babbage imagined something far more ambitious. His difference engine was designed to compute and print mathematical tables automatically. Tables were essential in science, navigation, finance, and engineering, but human tablemaking was vulnerable to errors. Babbage wanted a machine that could calculate values systematically and print them, reducing both arithmetic mistakes and transcription mistakes. The challenge was scale. His designs were so complex that building them in his lifetime proved impractical, and their size suggested the need for steam power. Still, the difference engine introduced a deeper idea: a calculator could be more than a tool for individual sums. It could be a machine for producing structured mathematical output automatically. In 1855, George Schutz succeeded in building a smaller, simpler model inspired by Babbage's difference engine. That success proved the idea was not fantasy, even if Babbage's own full vision exceeded the manufacturing resources of his era. Babbage's second great design, the analytical engine, reached even further. Begun in the 1830s, it is often discussed as a conceptual ancestor of the modern computer because it was not limited to one calculation pattern. A crucial step was the adoption of punched cards derived from the jacquard loom. In textile production, punched cards controlled woven patterns. Babbage saw that a similar method could control operations in a calculating machine. This meant the machine could, in principle, be programmed. It could follow instructions, use stored values, and perform sequences of operations rather than merely execute a fixed arithmetic routine. The analytical engine was mechanical, but its architecture pointed beyond ordinary calculators. It suggested a general-purpose calculating system. The tragedy and fascination of Babbage's work is that it arrived before the industrial environment could fully realize it. The ideas were there, but the machinery required extraordinary precision, funding, and persistence. The connection between Babbage's vision and 20th-century computing became visible in 1937, when Howard Aiken persuaded IBM to build the automatic sequence-controlled calculator, better known as the Harvard Mark I. Its architecture was influenced by the analytical engine, and when completed, some described it as Babbage's dream come true. The Mark I was not a small desktop calculator. It was a large electromechanical machine, but it embodied the transition from isolated arithmetic devices toward automatic computing systems. This is why mechanical calculators should not be treated as dead-end curiosities. They formed a chain of ideas and engineering habits that led toward programmable machines. Each generation had to solve questions of representation, sequencing, input, output, and error control. Even when electronics eventually replaced gears and relays, the conceptual problems remained familiar. The history of mechanical calculators is therefore not just about old machines. It is about the long effort to make calculation automatic, dependable, and scalable. By the 1960s, the mechanical calculator industry was approaching its final transformation. A symbolic milestone came in 1961 with the Anita MK7 from Sumlock. It was a comptometer-style desktop machine, but it became the first desktop mechanical calculator to receive an all-electronic calculator engine. That made it a bridge between two worlds. On one side were the mechanical traditions of keyboards, counters, and office machines. On the other side were electronic circuits that could do the same work faster, quieter, and with fewer moving parts. Once electronics became affordable and compact, the advantages were overwhelming. Mechanical calculators had improved for more than a century, but they could not compete indefinitely with electronic speed and miniaturization. By the mid-1970s, production of mechanical calculators had largely stopped, closing an industry that had lasted around 120 years. The machines had become obsolete, but not irrelevant. Their design vocabulary lived on in keyboards, calculators, computers, and the expectation that machines should handle arithmetic instantly. The mechanical calculator's legacy is easy to underestimate because its parts look old-fashioned today. Gears and drums seem distant from microchips and software. But the central ambition is the same: take a precise symbolic task and make a machine perform it reliably. Pascal solved the carry problem for addition. Leibniz created mechanisms that could support multiplication and division through repeated operations. 18th-century inventors proved the power and difficulty of precision design. The arithmometer made calculation commercially practical. Keyboard machines reshaped human input. Babbage expanded the dream from calculation to programmable automation. And later electromechanical and electronic machines carried that dream forward. Mechanical calculators remind us that computing did not begin with screens. It began with the desire to remove drudgery, reduce errors, and extend human capability. Every click of a gear was a step toward the digital world, and every modern calculator still carries a trace of those machines that once made numbers move. If you found this helpful, please like this video and subscribe for more explainers.